Hey guys, so this is where we concluded our previous discussion, and quite naturally we will begin here. Now, first thing first, I hope that by now you have desensitized yourself to this expressions here, because this is also one of the objective of this course, that when you find a numerical expression assuming these forms, you are fairly comfortable with it, and irrespective of where you come across these terms, you are ready to face them. Now, what we have essentially been considering is, getting back to our technical discussion, we were trying to rather deform a crystalline material by imposing a force. We made our life a bit more complicated by assuming that this crystalline system that we want to permanently deform exists in a force field, and this force field changes with time. So ultimately what it means is, now I'm imposing a force, I want to change the positions of the atom, and when the position of the atom changes, what essentially happens to my system is my system has permanently deformed. But unfortunately, the change in the position of the atom is not only dependent on the force that I'm imposing, but also it depends on the force field in which my system is already presenting, or is rather already present in. Now this is the force field that the force that I'm introducing, and this is the force field in which my system is already present in. So the combination of these two should essentially govern the resulting position of my atom, which is denoted by x of t. Now this here gives the mathematical description of the system that I am considering. My crystalline material present in a force field. I am introducing an external force so as to change the position of the atom. So all this can be mathematically expressed by this expression or equation here. The force that I am imposing, or the force the atoms experience, depends on their position and also their velocity, and this is the external force field, or this is the force field in which my system is already present. So when I solve this, I get a resulting position of the atom which is influenced by the force that I am imposing and also the force field in which my system is present. Now mathematically speaking, this is a linear non-homogeneous ODE. In order to solve it, in our previous discussion, we first assumed that this force field is rather zero or is insignificant. So when I make that assumption, my ODE transforms from linear non-homogeneous to linear homogeneous, and I use some street fighting mathematical techniques to come up with a solution. So this solution has two components. One is the solution has these constant and the lambda values, the so-called lambda values. In order to find these lambda values, the assumption that my force field was absent was helpful, but it is not what is there in the real world. My force field is very much present. So in order to accommodate for my force field, what we are essentially doing is we are changing the forms of K1 and K2. What essentially we are trying to do is, originally when I assume my force field is absent, these K1 and K2 were constant. Now since I have to introduce the influence of the force field, I am trying to accommodate the influence of the force field by changing these constants to time dependent variable. So ultimately my solution for the system wherein the force field is very much present, the K1 and K2 are no longer constant, they are time dependent variables. So I now essentially have two variables, so I can solve these two unknown variables through two expressions, and these two expressions we arrive at by one imposing a condition. It's called as a condition equation. So we introduce a condition equation, and we arrive at the next equation by ascertaining the first derivative, the second derivative, and introducing it in the original expression. I have two unknowns when I want to solve my linear non-homogeneous ODE. In order to arrive at that two unknowns, or in order to solve for the two unknowns, I introduce or I build two equations. One equation is called the condition equation, in which I am solving. The other equation is I arrive at it by substituting for my second derivative, first derivative, and x. And when I do that, I end up with these two equations. I can solve this, and ultimately I will be able to calculate my two unknowns K1 and K2, which can subsequently be substituted here, thereby rendering the solution of my non-homogeneous ODE, or to put it in the physical terms, these two terms, by substituting it, I will be able to find the positions of the atom, which are now governed by the force field in which the system is present and also the force that I introduced to permanently deform my system. Now towards the end of that previous discussion, I just mentioned that when the forcing term that we have, the force field that we are talking about, when it is numerically expressed, we call that as a forcing term. The reason it's called as a forcing term is because now the position of the atom is not only governed by the force that you are introducing, but also it is being regulated by, it is forced back to the existing force field. So therefore, too many force, I understand, but unfortunately that's the name that is conventionally used. So yeah, we have these forcing terms because they regulate the position of the atoms now, in addition to what we are essentially imposing. Now, when we have, or when the form of this forcing term is identical to that of the form of the solution of my ODE, I stated towards the end of the previous discussion that there is an easier route to adopt. So that is what we will be considering in this discussion here. Again, the forcing term here is of this form, and the solution that we get when I assume that this overall expression is homogeneous is of this form here. So there are two terms, and each of these terms are of the form similar to that of my forcing term. So when this condition is satisfied, when the solution that I have is similar to that of the form of the forcing term, then I can adopt an easier route to solve this non-homogeneous ODE, and that is what we will consider in this expression, or consider in this discussion. Now, when you consider, or when you look into the framework of a solution that you get when you have such an ODE, so you have an ODE wherein the forcing term is of the form that is equivalent to that of the solution. When you have such an ODE, of course it is non-homogeneous. Of course, we need to have an extended solution for it. When you consider the nature of the solution for this specific form of ODE, this solution have one additional term that brings in the effect of the forcing field. In our previous discussion, in our previous approach, we saw that the effect of the existing force field, the effect of the forcing term is introduced by K1 and K2, which are no longer constant but are dependent on time. When I change my K1 and K2 from their constant nature to K1 dependent on time and K2 dependent on time, we said that this introduces the effect of the forcing term. This introduces the effect of the existing force field on the position of the atom. Now, when I have my forcing term of the form similar to that of the solution, what we state that the effect of the forcing term is introduced by a third term that comes up with its own constant. The effect of the forcing term on the position of the atom is introduced by a third term that comes up with its own constant. So the effect of the forcing term is now introduced by this term here. This term has this constant K3 and adapts the same form or the same expression that of the forcing term. Again, my position of the atom is going to be influenced by my forcing term. My forcing term has the form similar to that of my homogeneous solution. When this condition is satisfied, I am assuming that my solution is going to have a third term which brings in the effect of the force field. And this term will have a constant of its own and adapts the forcing term as it is. Now, when I am able to find this constant, then my solution will have three different terms, two speaking of the homogeneous component that has already been solved here, and one that talks about the influence of the forcing term. Now, when I am able to find this K3, then I have brought in the influence of the forcing term, thereby solving for this entire non-homogeneous ODE. Now, in order to find this K3, what we essentially do is we take the first derivative of this expression here. Of this first expression here, we take the first derivative of it, and also we take the second derivative of it. Now, we have x of t, x prime of t, x double prime of t. All of these now can be substituted back to this expression here, to my original non-homogeneous ODE. So when I substitute all this back to my original non-homogeneous ODE, I end up having an expression like this. And now this expression is so convenient that we can cancel these two terms out, and thereby I end up having my K3 of the value 1 by 6. Now this K3 I can substitute back to my expression here. This K3 I can substitute back to my expression here, and then sum it up to these two terms to get the overall solution. Again, to have a quick recap, what we have here is a non-homogeneous ODE wherein the forcing term adopts a form similar to that of my homogeneous solution. When that is the case, I assume that the effect of the forcing term can be introduced into my solution by an additional term, and that additional term is this. And in that additional term, I'm assuming a new constant and I'm adapting my forcing term as it is. And when I adapt my forcing term as it is, all I need to do is find the value of K3. In order to find the value of K3, I take the first derivative of this expression, second derivative of this expression substituted, I'm able to find the value of K3. Now once I find the value of K3, substitute it here and sum it up along with this. So this gives me the solution for my homogeneous condition. This gives me the solution when there is a non-homogeneity. So ultimately, when I sum it together, I end up with this expression here, wherein the position of my atom is now governed by the force that I introduce and also by the force field in which the system is present. The terms that govern the position of the atoms with respect to the force that I introduce are these two terms here, and the term that introduces the influence of the force field is the term here. So when I have a physical condition wherein the forcing term assumes the form of a solution. So here in this case it is e power minus 5t. Now since e power mav, as we considered in our different discussion on different series, that this e power can also be equivalent to that of sin x and cos x. So basically, if even when you have your forcing term, you can adopting a form of sin x and cos x or sin t and cos t, you will be able to adopt the same approach here. And the approach here is, we assume that the effect of the forcing term can be brought in by an additional term in my solution, and that additional term has a constant and the same forcing term introduced in it, and all I have to do is find that constant, find it and sum it up to my homogeneous solution. And when I do it, I end up having a solution for my linear non-homogeneous expression that describes, or ODE, that describes my physical system. So I know this lecture is quite short. Why not? When we can have longer lectures, why can't we have smaller ones? So with this, rather, we will wind up, and maybe in the maybe as a preparation, so that preparation for quite a long lecture in the subsequent discussion, we will stop this lecture here, and we will see ourselves in the next discussion, wherein we will be considering a forcing term that introduces non-linearity in our ODE. Goodbye.